Hello, hi. My name is Neil Fan. I'm a co-founder of SciSig. We're doing hardware acceleration at SciSig. Yeah, so due to its very nice properties such as asynchronous and zero knowledge, ZKP is what everyone's eyeing right now, and we have a bunch of applications like ZK projects, like layer one privacy blockchain, layer two scaling solutions, and a bunch of other ZK applications building on the different chains. Yeah, but for hardware acceleration component, as you know, the proof system is evolving. Every year, we have a bunch of new proof systems coming out. And yeah, the latest one is a Hyperplug, and who knows what will happen in the future. Yeah, so to mitigate this issue, we ensure two design principles at SciSig. And the first one is we only optimize the most general components, which will be used in multiple ZK schemes. And second, we work on the lowest level components. Yeah, so and the intersection of these two things, I'll talk about here, is multiscalar multiplication and number theoretic transform. So that's the two components I'm going to talk about here. Yeah, so but before that, we were going to a more fundamental primitive called maybe a module. It's called modular multiplication. So that's used in both the MSN and NTT. And for the modular multiplication, a common practice here is to use Montgomery module to say Z equals XY modular R, and we can write it in this way. And yeah, so the formula we use to say this x prime equals x times r, and we can represent all other things in a similar way. And the key design in doing the Montgomery reduction or the modular multiplication is to say we use Karasuba here to reduce the hardware resource usage. Yeah, so Karasuba is a nice algorithm deal with integer multiplication. And second, yeah, since we are right now working on the FPGA part, to extract the resources on the FPGA, we use the NOT to reduce the DSP usage in this variable constant multiplier to make sure we can make every DSP in the FPGA counts. Yeah, so that's the most fundamental module will be used in both MSN and NTT. Okay, so now let's jump to the MSN part. The MSN, yeah, also the very normal algorithm you use here is a Pippinger algorithm. It's a nice parallelizable algorithm. Yeah, so here is a picture of how we how the workflow in our FPGA implementation is so the MSN will take the Gn and Xn as inputs, and the Gn is a vector of the points, while Xn are their coefficient. And we're trying to compute the multiscalar multiplication with respect to these two inputs. Yeah, so for here we have this a scalable MSN chain, which will distribute the input to each PE. So PE here stands for processing element. So it's a single computing module that can handle the some part of the multiplication. And yeah, they are somehow independent of each other, but they are still sequentially independent. Yeah, since when there will be some partial inputs coming out from the PE0, which will be passed to the PE1 and etc. And in the end, we have the final MSN output. So if we enlarge one PE here, we will have several sub components here, such as MSN, EC-ALU. Yeah, so yeah, I'll just list out all these sub components here. So this so in each PE, we have the ALU, we have the EC accumulate table, and we also have the table controller. So the EC ALU here is in charge of doing all the multiplications, and the EC table accumulate table is here to store the temporary results. And the table controller is to reduce the EC result in the table. And yeah, so there are the sub components we will rely on for each PEs. Yeah, so that's basically a hardware implementation of the Pippinger algorithm, and we put it on a FPGA. And if we zoom out a little bit, so that's some so the previous night talk about like one PE, but right now like we talk about how to put the themes on our FPGA. So for the FPGA, the key idea here is like we have like multiple FPGA on a PCB. So PCB stands for like printed circuit board, and we have like multiple PEs on a like per FPGA. So combining these like two key ideas, we can have like some tremendous performance compared with other players. Yeah, so like our MSM like performance is like our FPGA server is already online, and this like performance is already measured. We call it like Sonar MSM. So basically, it can run like 2 to the 30 MSM on BN250 for this curve like in around 700 milliseconds. So for here, I'm going to talk about BN254, since that's a curve like our ecosystem partners, they care about. Like we also do this like BRS like 377 and BRS like 381. But for here, I'm going to talk about the numbers here. So compare with the Cyclone MSM, like we are 70 times faster than Cyclone MSM and 200 times faster than the Pipe MSM. And yeah, so compare with the FPGA like champion from the Z-Press competition, like they are working on the BRS 377. We have the same number, like we also do that curve, and our comparison is like we are 62 times faster than there. But for the GPU track, like we are only like 11 times faster than the GPU track. Yeah, so like we are working on some like further improvement to see like if we can see if we can like reach like maybe 40 times speed up compared with GPU performance. And our FPGA is already online, and we are doing the final test and ramp up on the server. It will be open for test and integration to our ecosystem partners in the coming week. Yeah, maybe just in 1 week. Okay, so that's like one thing. The other thing here we talk about is NTT. So NTT, like we follow the Pipe ZK paper, we break this like large size NTT into the smaller size NTT. So that's also the common practice, like in doing the NTT acceleration. So for here I won't have time to talk about our like detailed design, but I just talk about some like some problems like we encounter during the design. The first one, like as you know, the NTT is a butterfly. They access the memory in a butterfly fashion, so it will be a very bad memory access pattern. So the solution here is like we can actually customize an intermediate data layout with like rewarder computation. So the CPU, the host, it doesn't need you to do this like post-processing on the output. And it will somehow increase the data access, while at the same time, there is like no need, as I said, to like reorder the outputs like after our accelerator, like for the accelerator. So that's a problem one. And second, yeah, since we are dealing with like very large entity, so like we have a very large like twiddle factor, and so how to handle this twiddle factor? Like one way to say is like maybe you can just store the twiddle factor on chip, so that will cause a lot of will count a lot of memory size on chip, and so that's not desirable. And second, you say maybe you can compute the twiddle factor on the fly, but the FPGA, their performance is quite limited, so that's also not desirable. So here we somehow combine the both. Like we mix the storing and the compute on the fly. So in that way, like we only need a small memory for the twiddle factor on chip, and with like very small memory, like we can do the computation while we do other computation like on the FPGA part. So combining these things, like we can handle this large size of twiddle factor. Yeah, so that's like some algorithm part, and for our design, like it's a multi-die FPGA like based accelerator. Like we rely a lot on the HBN for this like massive onboard bandwidth, since like there would be a quite high demand for the data transfer for the NTT part. And we do a lot of optimization on the ALU, which is like compute module, to saturate this PCIe, since the NTT is also like PCIe bounded. Like we need to do a lot of things to make sure our design is like a fully pipeline design. So it's a fully pipeline design to overlap the data transformation and also the computation. Yeah, so that's a picture to illustrate our FPGA design on the NTT. So like it will take the input, and then we have this like HBM which like connected multiple vector vector units about handling the butterfly. Yeah, so the HBM will like distribute the input to each vector unit to do the actual computation. So that's like some like very high level description or very high level overview of how we design the NTT part. Our NTT is not yet ready. Like we pinned down, like we finished like all the small modules, so we haven't do the final thing yet. Yeah, so like our estimated performance for 2 to the 26 NTT, for the 256-bit NTT is like around 27 milliseconds. And the current state of the art is based on the, like at least from our, as far as we know, the current state of the art is it's an open source library by Supernational, and it's like around 50 times faster than the CPU-based implementation. So compare with this like open source repository, yeah. So our like NTT will be like around 15 times faster if this is run on 3090 GPU cards, and it's like 13 times faster if it's run the 4090 GPU cards. Since these two cards they all use the same PCIe, so there would be just a very small difference running on the different GPU cards. So that's the estimate. Yeah, we call it Sonar NTT. Yeah, so it will be open for testing and integration by end of this. By end of today is March the 1st. So by end of this month. Yeah, so as you say, like we do FPGA acceleration, but how can we like beat GPU by a lot? So that's our last secret sauce. Like we actually like we put a lot. We design our own PCBs, and we put a lot of like FPGA chips on a PCB, and we do like interconnected these PCBs to extract the best performance out of this like FPGA. And these acceleration cards, like they talk to the host CPU through the PCIe. Yeah, so that's the FPGA server. And yeah, so like our current FPGA server will combine the MSN and NTT and also some miscellaneous such as weighted generation to put it on the FPGA part. Like we customized the whole FPGA server. Like we customized the high bandwidth interconnect and the PCB design, and also we do a lot of on the power delivery and water cooling. So that's a blurry picture of how the PCB will look like. And so this is our real server. So like the server is already online, yeah. So that's the FPGA part. But our ultimate goal is to do the ASIC. So yeah, so like we call it like Galaxy ZKP. It will be a 12 nanometer like ZKP ASIC, and it hopefully will be ready by in the second quarter of 2024. Yeah, so it will contain a lot of PEs, and in each PE, the most elementary component is modular multiplication, and it will be like in every PE. And we combine a lot of PE to get a PE cluster. Yeah, so that's a layout, the floor plan for like ASIC. If you like enlarge like one, the modular multiplication part is something like this. So we have like 16 modular multiplication in each PE. So that's the floor plan for ASIC. Yeah, so like the last slide is to say like we are building building a proving network based on our own hardware, and we will provide our service to our ecosystem partners. Yeah, that's all. Like if you please follow us on Twitter. Like we occasionally publish something there. If you have any question, like I'm here. Yeah.
Any questions for our speaker?
Mining, these are very impressive results, so congratulations. Mining is generally an energy game, so I wonder what does the power efficiency look like in all these benchmarks?
Yeah, to be honest, the FPGA server is very like costs a lot of energy on that. Yeah, so like one FPGA chip will be like around maybe 100 watts. Like we have like multiple FPGA chip on a PCB and multiple PCB in a server. So In the FPGA part, our performance, like the energy cost will be slightly higher than the GPU. But if we move on to the ASIC, it will be just a fraction of the FPGA energy cost. So like, yeah, so that's that's the answer. Yeah.
Let's thank our speaker again. Yeah, short one.
So because you give the same talk like yesterday in the ZK Day and later in Twitter, so basically there is a very popular question about this. What is the unit cost of this machine?
Yeah, I guess like I saw from the Twitter thread, like I also replied it there. Yeah, so like he said, like compare like our massive interconnected FPGA to like GPU is not an apple-to-apple comparison, but as you know, the FPGA actually is like quite like resource limited, but it's very flexible. So comparing the one single FPGA chip with like GPU cards is not a fair comparison. And for most customers, they actually don't care like what like hardware you are using. You can either use like GPU or like FPGA or like massive interconnected FPGA. Yeah. Minus the energy cost part. But yeah, so like we are trying to extract the most resources on the FPGA to say like we can actually use FPGA to achieve similar results of ASIC, and we can beat GPU on that front. Yeah.